Greetings and welcome, friends. Mr. Waddy here. Today we're going to talk about a whole bunch of properties of chords intersecting, or tangents or secants intersecting with one another. These theorems are going to come at you fast, so look out. Here it comes. Tangent and intersected chord theorem. So check this out. If I have a tangent line and a chord with which one of its endpoints is at that point of tangency, it forms two angles. All right, those angles you might think are a linear pair, and you are correct. And those two angles also form or intercept with two arcs, a minor arc and a major arc, that add up to 360. Now think about this. Here's my semi-fake proof. Those two arcs add up to 360. These two angles add up to 180 because they're a linear pair. This angle intercepts the arc and ends up being exactly half of it. 180 is half of 360, right? And yeah, then this right there, that arc is going to be twice the size of this angle. It's pretty great. It's a pretty great theorem. I recommend it. It's a good theorem. I would use this theorem for problems when solving them. Yeah, 10 out of 10 on this theorem. Good job, Euclid. Let's see. Actually, it's 10.14. Yeah. So you notice our theorem count is getting high. So let's see. Let's put this to use. Line M is tangent to the circle. Find the measure of the blue angle or arc. Okay, so what is this angle here? Right, it's going to be this angle doubled, right? Multiply by 2 to go this way. Divide by 2 to go that way. You can directly use that formula if you want, but I think that you guys are swift enough that you might be able to handle that like so. So these next batches of theorems require us to kind of or it's convenient, rather, for us to categorize these intersections in a few different ways. Okay, so there's a way for lines and circles to have the following outcomes, right, Holden? So lines can intersect on a circle, right? So that's the lines and the circle all had a point of concurrency. Lines can intersect inside of a circle, or lines can intersect outside of a circle. All right, it's also possible to just have a circle and then just two lines over here and they never intersect that circle at all. But we're not talking about that situation today. So it turns out that here's a whole bunch of theorems, and there's some ways to kind of see some patterns and relationships between these. But let's look at theorem 1015. So do the lines intersect in, on, or outside of the circle? Where do the lines intersect? Inside the circle. Okay. And it says the following, that if two lines intersect inside the circle, all right, there's a whole bunch of relationships with vertical angles and linear pairs, right? We know all that. But it turns out that this angle will be the average of its intersected arcs, all right, that are formed by those two, right, lines intersecting, right? So it is the average of those arcs. We did some Geometry Sketchpad work and came to that conclusion as well. And then angle 2 is going to be the average of its intercepted arcs. All right, so I think average is a good way to say it. If you want, you can think about it, right? Add them up, divide by 2, you get that as well. I also had a student recognize that if I add this angle and this angle, which are the same, they add to be the same thing as these two arcs do. One thing to point out is that this intersection is not at the center in this diagram. This is true no matter where I move that point throughout this circle. And yes, if it is at the center, this theorem would still apply, except then we would just have two central angles and the two arc angle measures would be the same as well. So the theorem does apply in that situation, but in kind of a reduced way, so to speak. All right, here's another theorem for you. All right, so here's an intersection outside the circle. And let's see. So if the intersection's inside the circle, okay, the angle was the average of them, or half the sum, and here the angle is half the difference. Okay, that's the only difference between these theorems. And look at how cool that is. It's already on your desk over there. You're welcome. As in your desk over there has it on it right now. All right. So notice that these lines could be formed with a tangent line and a secant line. It could be two tangent lines. It could be two secant lines. But the idea is it's half of the difference. So let's take a look at some examples using these. All right, friends. So here we go. Intersection inside the circle. That means x is going to equal the average of those two things, right? So if you want to do half parenthesis, or if you want to just do 130 plus 156 all divided by 2, whichever way you write that, don't matter none bit. So let's see, 130 plus 156. I'm reaching for my calculator. I plugged it in wrong. 286. Ooh. (143 degrees). All right, so that's kind of cool. Also, I want to point out, you will have problems where maybe we do know the this angle. I almost called it a central angle. Ladies, gentlemen, catch this. Catch this news. It might be possible that you know this and one of the arcs, and then have to find some unknown value here. Emmett, how would I do that? Exactly. So, right, I would have an unknown here, and I would know this value. I would plug it in the equation and solve for my unknown. Let's see here. I've got an angle outside the circle. So x is going to be half the difference. I'll write it with parentheses this time. Which order should I subtract these in, do you think? It's always going to be the big minus the little. All right? So 178 minus 76. That's going to be half of, looks like 1 dose. So is that going to be 51 degrees? Yeah, not bad. So I want to point out that it's possible you might know this and not know one of those. You're going to have to plug those into the right spot. Don't assume that it's always the unknown that is going to be on the other side of the equation. Actually, just to show that, let's do the monitoring progress questions 4 and 5. And let's actually have you guys do them. I'll be around to help you. Just do the setup for me. If you want, you can solve it. All right, friendly friends. So, this tried to sneak you. Look out. First of all, we can only relate it to this angle here. These two angles are a linear pair. So this one is 78 degrees. And I cannot say that y is half of 78 and 95 added together. 78 is the average of y and 95. Okay, so that would be your setup. And then if you wanted to solve, you could either distribute or multiply both sides by 2 first, and then end up subtracting from both sides. Okay, for this one, what would I do? What would my setup be? This one, the intersection's on the outside? Nope. So 30. So the angle is equal to half the difference of the major arc and the minor arc. So this time the variable goes here. I want to notice that because subtraction is not commutative, that if my unknown was here and I had this as like some known value, then I would have to change the order of that as well. So the setup you have matters. Here, we'll solve this one for fun. We're here. We'll solve this one. So I'm going to double both sides rather than distribute. I'd rather kill fractions than work with them, you know? I'm sorry. That might be a terrible thing to say about those numbers. But I know you guys all know it. You guys all like whole numbers and integers far better than fractions. No? Pythagoras would disagree with me. So yeah, so we end up getting a equals 104. Beep, beep. Right. So that's not too bad. Hey guys, here we go. Let's see how articulate I can be in describing this word. So Holden and Ryan, let's talk about this. A circumscribed angle is an angle whose sides are tangent to a circle. And we've had theorems relating the measures of angles. Let's see what happens here. So this is actually similar to the one that we were just looking at. So it says the following, that the measure of a circumscribed angle is equal to 180 minus the measure of the central angle. What? That intercepts the same arc. Wow. Okay. That's crazy sauce, guys. So this angle ADB, all right, is equal to 180 minus the central angle ACB. Now, I'm going to assume this way. Let's see, we'll have to experiment. Or is it that way? Which way do you guys think? 180 minus this would give me an acute angle. 180 minus that would give me a negative angle. Yeah, we probably don't want negative angles. So notice, so here's a central angle. They both intercept the same arc. Okay. And so if I want to know this, it's just going to equal 180 minus the central angle, or 180 minus this arc length. Cool. Let's put it to use. Man, we're learning so many theorems. Okay. All right, I think I might have been thinking about some of tomorrow's theorems. Today we're only talking angles, it looks like. Yeah, whatever. So find the value of x. So guys, here x is going to equal 180 minus 135. X is equal to 45 degrees. Nice. Okay, over here. Sneaky. All right, this is not a central angle, first of all. This is a central angle. Okay, what is the measure of this arc, EF? Okay. All right, let's work with that first. So I'm going to call this Y, maybe. Wow, this one's a nice problem. So what do we have? We have that 30 is going to equal 180 minus Y. You agree? I'm making a half step before I even think about X. Let's solve this. So subtract 180 from both sides. I'd get like negative 50 equals the opposite of y. So y equals 50. Okay? Did I done do that wrong? I done did that wrong. That's good. So if the central angle is 150, the measure of this arc is 150. How do I relate that to x? X is going to be half of it. Right? Because x is an inscribed angle that intercepts that arc. It is half of its measure. So x is 75. That's a good problem. That's pulling in a few skills for you there.